So let me see if I can pull up another page here. So it's non-viscous or inviscid. Or inviscid, which means that you have to understand what viscosity is. Viscosity is when you have internal forces acting on a fluid, okay, as well as external forces, okay. So if I look at this jar, you know what, I want to bring something in. Let me see if I can do this. I'll bring the picture in just a second. But if I look at this jar here, this jar has internal forces. It keeps it bound. I mean, it keeps it bound. Okay, so it's water that's going to be in the jar, but it could be anything. It could be honey. It can be oil. It can be, but those things are, they're not just, if they're not in the jar, they're not just going to separate. They're going to still kind of collect together on the ground. Even though they might separate, they still will collect in pools. So this has to do with internal forces. But then you have external forces, which are the interaction between the water and the surface of the jar, okay? So these both lend to viscosity. If a non-viscous fluid wouldn't have these things, okay? So basically that fluid wants to flow, but something else is holding that fluid back from flowing at its full potential. That's the idea. So that's one of the things that Bernoulli's equation doesn't necessarily include. So we need a way to check to see how good we are at predicting the flow of velocity outside of this particular bottle. Okay. So let's just see if we can look here. Just gonna say done, and you'll see that we have ourselves a plastic container here. It's just a 2-liter bottle, okay? The way we're gonna maintain the velocity here at 0, I think this was our V1. The way we're gonna do that is by having a source of water continuously replenish the fluid. All right, so we have a reservoir. So this container appears like a reservoir. All right. And now we can calculate the initial velocity, or the velocity coming out of the orifice, using this equation. This is V sub 2 equals to the square root of, oh, I can't remember. Oh, wait, no, I don't need to do that. Let me just do this. Oh, square root of 2gy1. 2gy1. Now we need a method to make sure we know the velocity, the actual velocity coming out. And we are very familiar with the method already. And these are the equations that we've used before. And we're just going to use them again. We have similar conditions, and I'll just put YF minus Y initial equals to V naught sine theta times T minus 1/2 GT squared. I'll just use these same 2 equations. One is for time, the other one is to calculate the initial velocity. So we're going to calculate the initial velocity, or the velocity emanating from the orifice, like this. And we're just going to divide it by time, where time is going to be equal to the square root of a -2 YF minus Y initial over G. We're already familiar with this. So we're using a technique that we're very familiar with. We did it so many times. We use it here. The water, I know it's a fluid, but water is actually a bunch of little particles. Okay, so we can consider it as a particle, even if it wasn't a bunch of little particles, but we can consider this as a particle, and we can assume that this particle is eventually going to go down here and hit this location. Okay, so we're going to go into the experiment now.